All right, so I'm going to start talking about acids and bases. This is our last major topic, and really it's going to turn into more equilibrium. That's okay. We already have a good, strong foundation with the fundamentals from last chapter. All right, now there are some new changes to the AP curriculum. They did take out one of the definitions of acids and bases. If you remember from Honors Chem, we talked about some of the different definitions of what an acid and a base are. I'll review them here real quickly and then maybe a little more slowly. So we have, at first, when we were classifying acids and bases, we went by the Arrhenius definition. The Arrhenius definition applies to ions specifically in aqueous solution. So the way I kind of remember this is it is aqueous Arrhenius. And in the Arrhenius definition of acids, acids produce hydrogen ions. So those H plus ions is what defines an acid. As long as those are being released in a water-based solution, you have an acid. The Arrhenius definition for a base is that bases produce hydroxide ions when dissolved in water or in an aqueous solution. So those OH negative ions are increased when you put an Arrhenius base in water. But it had its limitations. It was limited only to aqueous solutions. So what we did is we kind of made a different definition. It's not exclusive. Arrhenius definitions or Arrhenius acids and bases still classify as acids and bases under the new definition. And I'll get to that here in just a second. Only one kind of base, and we're going to talk about ammonia here. Ammonia is classified as an Arrhenius base because it increases the concentration of hydroxide ions, and that is what we just talked about here in the definition, when you put it in water. Because what does ammonia do? It steals hydrogens. And if you put ammonia around water, it is going to take a hydrogen from water and become ammonium. That's what ammonia loves to do. And if you take a hydrogen away from water, you're left with hydroxide ions. Now, ammonia is a weak base, so it ends up going back and forth and setting up a little equilibrium. It's a struggle, a fight over the hydrogens. Ammonia over here, it steals a hydrogen from water and becomes ammonium, and then we have hydroxide. Then the hydroxide tries to take the hydrogen back and forces the reverse reaction to happen, and we have those happening at equal rates at equilibrium. This has been an AP chemistry question. It was even one that I put on the honors addendum for honors chemistry. So it said, criticize the accuracy of this statement. It said ammonia classifies as an Arrhenius base. And the answer that they wanted needed for you to prove that you knew, one, what the definition of an Arrhenius base was, and what ammonia did in water to increase those hydroxide ion concentrations. All right, so that is the first definition. Arrhenius, remember, had to be in aqueous solutions. But like I said, we found things that acted like acids and bases, but they weren't in aqueous solutions. So we just came up with a different definition. And that definition are Bronsted and Lowry acid-base definitions or terms. So we use proton donors and proton acceptors to distinguish between an acid and a base. A Bronsted and Lowry acid is a proton donor. Now, a proton is still a hydrogen, and I'm going to show you why. If we just look at drawing a hydrogen atom, in its nucleus we have one proton, but no neutrons in the most common form of hydrogen, and then it has its one little electron out here. If we make it H+, that means we're removing an electron, and so the only thing that is left is that one proton. And that's why we call H+ a proton. So or why we refer to it here. So an acid is a proton donor and a base is a proton acceptor, and they always are going to come in pairs. We'll talk about the product side of the reaction here in a second. So hydrochloric acid is an acid, obviously. When it dissolves in water, it gives its proton to water. Remember that we need to kind of look at H plus. Hydrogen ions are going to be very, very similar to hydronium ions. That's because this H plus is real attractive, and when it is in water-based solutions, there's going to be a lot of water around, H plus isn't going to exist alone very long, and if it's around a lot of water, it's going to become hydronium ions, and that's just a more realistic way to represent hydrogen ions in aqueous solutions. So, but really, this is going to indicate an acid to you, and the presence of this also indicates an acid. So, if we look at the dissolving hydrochloric acid in water, what we'll see, and we can label our Bronsted and Lowry acid and base, these are going to be reactants. And the way to look at it is you insert the phrase going to. So of hydrogen chloride or H2O, which one is going to, as the reaction proceeds, give up its hydrogen? And that is HCl, because you can see it over here just becomes Cl negative. It's lost its hydrogen. So this is my Bronsted and Lowry acid. Now, which ion is going to accept that proton? Well, water is going to accept it and become hydronium. So this is my Bronsted and Lowry base. And that's always how you're going to identify those. In this case, water does act as a base. It can also act as an acid. If we look at the previous slide, and water does donate a proton in the previous one. Let's look at that real quick. Here we go. Water ends up losing its proton as this reaction proceeds forward. So here it acts as an acid. That's because water, we classify it as amphoteric. It can act as it can act as either an acid or a base. Now, water isn't the only example, but it is one of the better examples, or more common examples. All right, so we've labeled our Bronsted and Lowry acid and base, and those are going to be reactants. On the other side of the equation, we can identify our conjugate acids and bases. And my little definition to make it easy to find the conjugate acid is that you follow the hydrogen to find the acid. I know it sounds a little strange, but in this example we have the Bronsted and Lowry acid and the Bronsted and Lowry base. Follow the hydrogen. Where did the hydrogen go on the product side? It went to hydronium, so this is my conjugate acid. And that makes Cl negative my conjugate base. Now, you can also look at it, if you look at the reverse reaction, which one is going to donate its proton, and in the reverse direction, hydronium does donate its proton to chloride ions. All right, now the next slide really just kind of sums up those acid-base pairs, and often on the AP exam they will ask for what are your acids in the following reaction. If they say something like that, they want both the acid and the conjugate acid. It's same thing if they ask for the bases in the following reaction. They want both the Bronsted and Lowry base and the conjugate base. So I have here a general equation. We have HA, which is what we use to signify an acid. It's kind of funny. And then we have our base. And the acid's going to donate the proton to the base, and you end up with your conjugate acid and your conjugate base, just like in the example I showed you. Now, this is an equilibrium. There is competition for that hydrogen. It goes back and forth, both forward and reverse direction. And that's going to be the basis for why I started here in the beginning that acid bases is really a whole lot of equilibrium. We're going to be dealing with weak acids and weak bases, dealing with equilibrium. So there's a competition for the hydrogen between water and those that conjugate base. The stronger base controls the direction on whether we have more of the acid and water or more of the conjugate acid and conjugate base, on where that equilibrium is established. If water is a stronger base, it takes the hydrogens and the equilibrium is shifted to the right. So we will be involving more equilibrium, and hopefully it'll just make the whole thing make a whole lot more sense. Now I'm going to do another little section here talking about pH, but I think I'm going to do that in the next video.